Hello, I'm Diego Irureta, and this project is Frozen Clip as a pixel gate for GUI agents. The problem I'm looking at is GUI grounding. Given a screenshot and an instruction like click the export button, where should an agent click? Strong systems like OS Atlas use a large vision language model on the full screenshot. That works well, but it is expensive. Every click requires rereading the whole screen, even though the target is usually a tiny region. So the core question is, can we cheaply route pixels first and only send the expensive model the region that matters? The approach is intentionally simple, and it's training free. I take a frozen clip model, tile the screenshot into a grid, crop each cell at native resolution, and compare each crop to the text instruction using clip cosine similarity. The highest scoring cell can be used as directly as a click prediction, or the top case cells can be merged into a crop and passed to stronger downstream grounder. The idea is that clip acts as a lightweight pixel gate. Route first, crop when confident, and escalate when it's uncertain. The top row in our poster shows the main results. On screen spot, the direct frozen clip router reaches 32.4 accuracy with the 16 by 16 grid, while committing only to 0.39 of this screen area for the click. Course-defined cascade improves that to 37.7, while using fewer clip passes than a full fine grid. And as a sanity check, anti-routing, which clicks the least similar cell, gets only 1.2. So clips ranking is not random. It really carries the instruction-specific localization signal that we are looking for. The left column shows the router itself. The input is a screenshot plus natural language instruction. The router creates a native resolution crops, scores them with clip, and chooses the best region. The important detail is that native crops, each cell is resized into the clip's input size, so small UI details get more effective resolution than they would in a single full screen pass. The middle column explains the accuracy and compute trade-off. The Pareto plot shows that the cascade is a better operating point than flat per crop routing. It gets higher accuracy with fewer clip passes. The formula shown is the routing rule. Score each crop against the instruction, and then use the top score margin as confidence. High margin would mean that one region clearly stands out, and if not, it's the other case. A low margin means that the router is uncertain. One of the most important findings of this study is the ceiling. Then single pass mass clip is about 53 times faster, but only reaches almost 10% accuracy. That tells us that the bottleneck is just not the semantic alignment, but it's also the per region detail. GUI targets are small, and the model needs enough resolution in the right place. The right column shows why is this useful as a VLM gate. OS Atlas on the full screenshot gets 80%, but if we give OS Atlas only the top 4 crops, it gets 61%, which is 76% of the full accuracy, while forwarding about 37% of the screen area. In a small standard resolution pilot, this also cuts visual tokens by about 60%. The confidence gate escalation curve shows the next steps. Use clip margin as a budget, and a high confidence stays crop, but low confidence screens get full VLM context. And this would be random escalations. 50% VLM calls, margin gating gets 61% versus the 56% on random escalations. The limitations are clear. Clip is much better on text targets than icons, 50% versus 12%. And on the 4K ScreenSpot Pro, direct routing drops 7.7%. Thank you very much for listening.